the second derivative. So the second derivative is all about the concavity of the curve. So let's draw up a curve. So could have something like that. And when we talk about concavity, it can either be concave up or concave down. So we can see that this part of the curve is definitely concave up. And this part of the curve is definitely concave down. So all of this part is concave up, and all of this part is concave down. This is concave down, and over here we have concave up. And mathematically what that means is that when the curve is concave up, that's when you're going to have your second derivative will be greater than 0, so it'll be positive. Whenever it's concave down, your second derivative will be negative or less than 0. Now, if it's concave down here and concave up here, where does it change concavity? Where does down become up and up become down? Well, that happens somewhere in the middle here, and we call that the point of inflection. So somewhere in the middle here, we're going to have concavity changing. So concavity changes here. And where that concavity changes, we call that our inflection point. And mathematically, that's where our second derivative equals 0. And we're going to look at how we can use our second derivative to find these inflection points on a curve. Let's have a look at an example. We're going to look at the curve y equals x minus 6 times x plus 2 times x minus 2. Expand it out, this will give us x cubed minus 6x squared minus 4x plus 24. I'm going to graph it out just so we can visualize what's happening. But you'd be using the first and second derivatives to graph it out yourself. So these will have intercepts at minus 2, 2, and 6. And we get something looking like this for our curve. So we know we've got stationary points here and here. And hopefully you can see that we've got concave down here and concave up here, and we're expecting our inflection point to be somewhere around there. So how can we use our second derivative to find that inflection point? So first we need the first derivative. So we'll get 3x squared minus 12x minus 4. Then we just find the derivative of that to get our second derivative, to get 6x minus 12. And we just learned that for an inflection point, your second derivative needs to equal 0. So we're going to do that. We're going to let our second derivative equal 0. So 6x minus 12 equals 0. And we solve for x to find the x coordinate of the inflection point. So we'll add 12 to both sides, divide both sides by 6, and we get x equals 2, which is roughly what we're expecting. So it actually happens on the x-axis there. So we'd need the y-coordinate. Well, we know the y-coordinate is 0, but if you wanted the y-coordinate, all you'd have to do is sub x into the original function. So we just sub 2 into the original function. And if you did that, you'd get y equals 0. So what it's saying is we're expecting an inflection point at 2, 0. But always with inflection points, we need to actually test if the concavity is actually changing across it. We can see from our graph that it is, but we always need to do the test ourselves. And to do that, we need to make a little table between x values and the second derivative values. So let's go ahead and do that. So we want to test what's happening on either side of 2 with the second derivative. So we know if we sub 2 into the second derivative, we get 0, because that's how we got it. So let's test on either side, 1 and 3. So if we sub 1 into the second derivative, we just have 6 times 1, which is 6. 6 minus 12 is minus 6. If we sub 3 in now, we'll have 6 times 3 is 18, minus 12 is positive 6. So what this implies is that on either side of 2, our possible inflection point, we have a negative value for the second derivative, which means we have a concave down section. And then on the right, we have a positive value, which implies a concave up section, which means that we're going from concave down to concave up. So that definitely shows a change in concavity. So we can say, therefore, concavity changes. So therefore, 2, 0 is an inflection point. And you can actually use the second derivative to test the nature of stationary points as well. Because if we got the x value of the stationary point and subbed it in to the second derivative, we'd get a negative value, which shows it's concave down, which means it's a maximum stationary point. And if you subbed in this value for your stationary point for x, we'd get a positive value for the concavity, which shows a minimum stationary point. So we can make a note of that as well. So if you have your x value of your stationary point, you can sub it into your second derivative. And you'd have two situations. If it was positive, it would mean concave up and a minimum turning point, or if it was negative, it'd mean concave down and a maximum turning point.